Welcome to Innovate and React. In this episode, we will discuss how metal organic compounds can be used to improve the production of electronic components. I'm very happy to welcome Dr. Leonardo Santoni to the show.
Hello.
You studied this topic at UCL in London and are also a science content creator. So welcome, Leonardo.
Hello, everyone.
Yeah, so maybe we start with a short background of yourself. What did you study and yeah.
So I am a postdoc based at UCL, and I did my PhD here in Caroline Knapp Research Group, and it was focused on metal organic deposition and precursor design of complexes for metal deposition on substrates. And I did 3-year PhD, finished it, changed the group, and now I'm doing a postdoc more focused on polymer synthesis and modification for membrane applied in fuel cells or filtration. In my case, like my specific research is more on the filtration side.
Yeah, still very interesting.
Yeah.
We used ultrafiltration kind of membranes.
Yeah, kind of. Like what I'm focused on is more the chemical filtration rather than physical. So once we modify a membrane with specific molecules, microcycles, we can maybe tune the membrane and target specific molecule. So when you have two molecules with the same size but different chemistry, with our membrane, hopefully, we can select directly one molecule and filtrate.
Yeah, interesting. My colleagues at uni
Hopefully.
used also membranes to filter out the catalyst from the reaction.
Oh, nice.
But
That's nice.
yeah, that's a different topic. Today we want to talk about
Yeah.
the metal deposition. So, what is this metal deposition in the first place?
So metal deposition is used to deposit metals on substrate and form thin films of conductive metals. Why do we do this? Because we want to, let's say, use this conductivity, these thin layers, conductive, in printed electronics or solar cell. These, let's say, not very new field, but still the state of the art of the metal deposition use silver, that is quite expensive. Copper is quite common. So in our group, we focused on aluminum deposition because it's a recyclable material potentially. The aim is to make the deposition, let's say, more sustainable. So we focus on the inkjet printing.
So you can basically
Um,
print the cables on these
yeah,
electronics in a very simplistic way.
yes. So the standard, the status quo, I would say, is more depositing metals with either CVD, if
What is
someone is
CVD? Yeah.
familiar with it, chemical vapor
Okay.
deposition, and or other techniques that requires high temperature, around 1000 degrees, sometimes high pressures. It's an expensive setup if you
Yeah.
think industrially.
Energy wise, it's
So
very.
yes,
Yeah.
plus the metal not always can be recovered. Sometimes it's expensive, so it's a bit a
Yeah.
tricky situation. So the aim of this group is to use aluminum that is cheaper, and potentially we can reuse it. And our aim is to deposit this metal at a temperature around 200 degrees, 150 degrees. It's very challenging. Yeah.
Still, it's a lot of saving if you compare it to the 1000.
Yeah, but also very challenging because aluminum is famous to form
Yeah.
oxides in a very easy way, and they're not conductive.
Okay.
So that can be annoying. So the aim is to try to find a precursor that allow us to deposit aluminum at a low temperature. Why this low? Because if you think about plastic and paper, be like above 150 degrees, often polymers decompose. So if we keep it lower, then we are able to print these conductive layers on a polymer without decomposing it. And that's an ideal situation.
Oh, great.
So the group does research on different metals, also silver, also copper. Caroline Knapp published many papers on that. They have also like tattoo-like circuits, let's
Okay.
say. So you can literally have something like compatible with the skin, I would say. Again, it's all preliminary studies, so I don't want to
Yeah.
say that we have invented the conductive
Yeah.
tattoo, but this is the potential of the printed electronics, let's say. What is a precursor?
Yeah.
For the people that don't know, because I mention it quite a lot. So a precursor is a molecule formed by the metal, in our case, aluminium, surrounded by ligands of different types. We don't have an aluminium carbon bond in this case. We have aluminium organic molecule around. So aluminium nitrogen, aluminium oxygen. The trick is to find the right complex with the right geometry and the least number of ligands in order to then deposit it. So the aim is I assemble a
Yeah.
complex with specific ligands. I form it. So I choose the ligand. So hopefully I know the chemistry of that and I can predict how it's going to decompose.
Okay. So.
So then I take this ligand in solution, I deposit it on a substrate. We also do spray deposition. So you spray it on a substrate, you heat the substrate, and your ligands will break the bonds with the metal and will evaporate. And your metal will be reduced and deposited on the substrate.
And then it ideally is just a metal itself without any impurities in between.
Exactly.
Yeah.
Ideally. So what you have to consider is the atoms in your ligands. So you don't want chlorides because they might contaminate your final film.
In what way? Do they then form metal chlorides or?
Yeah, like they stay
Yeah.
in the layer, so they're not good, like in terms of they can alter the conductivity, and it's difficult to get rid of these kind of atoms. And that's it, really. Like you want to use small ligands, as small as possible, because if you have too many ligands or too bulky ligands around your metal, then your decomposition temperature increase. So it's all about finding a compromise between the, let's say, smallest complex, but also more stable, less
Yeah.
reactive.
Yeah. Okay.
Because the problem with aluminium is that currently, if you want to deposit aluminium layers, you can use complexes that are very good for aluminium deposition. They're called alanes. The little problem is that they're extremely reactive and
Oh,
pyrophoric.
so they catch
So you
fire.
need a
Yeah.
glove box, you need to store them in cold temperatures, and it's not something you can really
Yeah.
scale up in a company. So that's why the compromise. So we want to have something more stable.
But still unstable enough that it decomposes. Okay.
Exactly.
So
Exactly.
do you have, when you use these precursors, you have them in a solvent and then you spray the solvent on? Do you have to first evaporate the solvent and then the ligands? Or basically you have a complex on the surface that then gets decomposed, or is it already decomposing in solution and you have nanoparticles?
No. The complex should be stable in solution as well. So you deposit it on the layer first, and given that the layer is heated while you're spraying, then basically the solvent evaporates, and with it the parts of the complex,
Okay.
because the heat is going to break the bonds between metal and
Yeah.
ligands, right? So then they just evaporate.
Okay.
And also we do inkjet printing, so literally printer printing with an inject.
But already
Yeah,
on the hot surface, so it's not you apply your solution and then you heat it up. You do it in already a heated, on the heated surface.
already a heated
Okay.
surface.
And
Yeah,
then,
it's already a temperature. Then we leave sometimes to sinter,
okay.
and then we repeat the procedure, adding layers and layers and layers.
Basically, then like a 3D printer where you also add layers.
Kind
Okay.
of, yeah, with a
Yeah.
human doing it. Yeah.
Interesting. I think that's also a very neat way to use these metal organic compounds, because you can very well define the complex and know how it looks like in like also the room of like what room it takes. Right.
Yeah, yeah. So the aim is we try to select, let's say, the more versatile ligands for the complex, so we can tune the ligand and study the properties. So in my case, in my PhD thesis, what I did, we use beta ketoaminates. They have quite a basic backbone, but then, and you have nitrogen and oxygen. And on the nitrogen, we are able to add a substituent that can vary from the methyl to the deep ACNAC, the isopropyl phenol. And these these allowed me to try to understand the properties of the final complex depending on the bulkiness of the ligand. So with a methyl substituent, maybe you will have more ligands around the metal because you have more space, and maybe the temperature it's lower than something like a phenol ring, right? That it's bulkier. Or I used terbutyl on the nitrogen. That's quite bulky as well. So then what I found in my PhD thesis, given that these precursors were not, let's say, ideal for the deposition, but
Why not?
because because I obtained different classes of complexes, and some complexes were not really suitable for deposition because I had lithium in it.
Okay.
Some other complexes ended up being lithium cages. Actually, this paper is going to be published very soon, and there was no aluminium in it, but the structure was very interesting. And some other, they contain a lot of aluminium, but then when we went to study the decomposition profiles with TGA and try to deposit it on the layer, then it was a bit more complex. So the method should be like optimized, maybe revise the ligand and things like that. So like while doing my thesis, I realized that I was more interested in the precursor design rather than the actual
Yeah.
deposition,
Well, okay.
because playing with the ligands, I realized that I found different classes of compounds. And so I was like, okay, can we predict properties from the size of the ligands? Spoiler, not
Yeah.
really.
That's a shame. Yeah.
But yeah.
Yeah, that would be cool if you can just
Yeah.
apply this very easy concept and then see, okay, this will work.
Yeah.
But
I mean, I'm making it
yeah,
very
yeah, of
easy
course.
now, but like, yeah, for the audience.
But the lithium comes from the ligand, right? So
Yes.
how would you usually get rid of it?
No, wait, sorry. The lithium doesn't come from the ligand. So in my project, I was focused. So basically, to make this complex, what do we use? The ligands and aluminum source. My first aluminum source is called TMAA. It's an alane. So you have aluminum hydrides bonded with 3-methyl amine. So that's my first aluminum source, and that's quite good. Technically, you could use directly TMAA to deposit aluminum, but as I said before, is extremely
Yeah.
reactive. So we want to move away from that and do something more user friendly. So that was one source. Then, while playing with my molecules, I realized that there was someone that made this precursor from lithium aluminum hydride instead of TMAA. So I was like, given that lithium aluminum hydride, yes, it's reactive, but milder, why I'm not trying it? So I went down that road, and I found out all these classes of complexes, and that's where the lithium come from.
Ah, okay.
So sometimes with specific ratio, the lithium goes in your complex. Some of the times you can maybe drive the reaction towards formation of lithium chloride, so your complex is safe.
Then okay.
And yeah.
So that was because you used a different aluminium starting material,
Source.
aluminium source,
Yeah,
right? So
yeah.
the and then you investigated these different kinds and tried to attach different ligands to it.
Yes, yes. So I tried terbutyl beta ketoaminate. I tried deep beta ketoaminate. I tried smaller ligands. There was some previous
Mm-hmm.
work done by a previous PhD student. We tried mesotyl ketoaminate. We tried different
Mm.
bulkiness, and yeah, we found out these various classes. And this work actually is going to be
Mm-hmm.
published soon. I found these chelated
Mm-hmm.
illuminates that are interesting because it looks like you have aluminum 1 complex, but it's not. I had this discussion with many scientists, and you realize that the ligand behave in a different way. So instead of being monoanionic, it's dianionic.
Mm-hmm.
So the aluminum is aluminum 3, and you have these lithium inside it.
Inside the complex.
Yeah, inside the comp. And that was interesting because then I was like, oh, nice. What if I swap the lithium and I put another aluminum or another metal?
Mm-hmm.
But yeah, I didn't have enough time. So for now, it didn't
Yeah.
work. But maybe, who knows? The next PhD student maybe will try this. Then I found lithium cages. Then, with a colleague of mine, we just got a paper accepted in Nature
Oh,
Communication.
great.
Yeah, so we managed to make the first non-pyrophoric
Mm-hmm.
precursor for low temperature deposition. It, it has been accepted, it's going to be released soon, so stay tuned for that. There is a preprint online that you can
Yeah,
find.
then I can put that
And
also in the show notes.
oh, yeah. And we found with other
Mm-hmm.
ligands that there is a
Yeah.
way,
Yeah.
let's say, but it's still
Yeah.
preliminary results. So a lot of unsuccessful reactions.
Yeah, I guess that's what the PhD always has. If everything
Yes. Not only.
would work directly, then it would be too easy, I guess. But
Yeah. I mean, I wish it was too easy, but
then everyone could do it.
yeah, also true. Also true.
Okay, so
But yeah.
once you have this ideal complex, then did you also investigate on how they decompose, or did you just characterize the
Yeah.
complex and?
So first you characterize the complex. So NMR, I was focused on the single crystal
Mhm.
XRD. My second supervisor, Jeremy Cockcroft, is the expert on it, let's say, quite popular in the field. And so the aim is, yes, great, you made it. Now grow a single
Oh
crystal.
yeah.
For the people that do this chemistry, they will understand me. It's painful. You try your best, different techniques, and then you
Yeah.
pray. Whatever you believe in, you pray. And I managed to have the single crystal for 5
Mhm.
complexes. That's how we define these classes. And then you study the decomposition
Mhm.
profile with thermogravimetric
Mhm.
analysis. So TGA, we realized that the decomposition temperature was still quite high for some of them, around 300 degrees. And so we were not really happy. Like, it was pointless to implement a deposition already when your decomposition temperature
Yeah.
is quite high. So yes, we did some testing and something, but there's still work to do on
Yeah.
the like material application of that,
But did you
let's
see a
say.
trend in your different complexes that what had an influence on the decomposition temperature?
Not really. I mean, you know that less bulky materials decompose at a lower
Mhm.
temperature. Sometimes we had the deep ACNAC. This ACNAC is the short name for beta
Mhm.
ketoaminate, and I formed this complex with 2 ligands, the aluminium and 1 aluminium hydrogen
Mhm.
bond, and that, even if the ligand is quite bulky, that decomposed at a quite low
Mhm.
temperature. Interesting, but the compound already existed. It was never used as a precursor. But again, on this we have to
Yeah.
study more. For now, we have just preliminary TGA analysis to have an
Mhm.
idea. let's say size matter in this sense, like less number of ligands and smaller ligands will bring your temperature down, decomposition temperature down.
Yeah, because of the orientation of the ligands and
Yeah. I mean, sometimes they affect the actual geometry of the vinyl complex, right? Because when you have a bulky ligand, it doesn't allow the other ligands to access the metal. But we can't really predict yet everything, let's say. Even ratio wise, like as soon as you change the ratio of your starting material, you form a different
yeah.
complex. So sometimes I had I don't know, terbutyl ligand ratio 1 to 3, so 1 equivalent of aluminium source, 3 equivalent of the ligand, you get, I don't know, trace complex. 1 to 2, you get a lithium cage. 1 to 1, you get chelated aluminate. So it's
Yeah,
wild.
okay. And what you wanted would have been the chelated aluminate, or were they too
uh,
strong?
in the first place,
Yeah.
no. We were not expecting it. But then when we found out, when we found it, we were excited because the chemistry was quite new. So in the literature, you often find these beta ketoaminate being chelating, -1, mono. It was quite
Yeah.
new, the dianionic character of the ligand, let's say. No, I was not the first one. I found only one paper mentioning it on a sentence, but that was interesting, like from a
Yeah.
chemical point of view, because I'm a synthetic
Yeah.
chemist, so I'm quite excited on that side. But by mistake, serendipity,
Yeah, that
because it wasn't a
yeah.
mistake, to be honest. It was on purpose, but let's say serendipity.
It also could have not worked, but then it's
Exactly.
always trial and error kind of, and then you get lucky with some stuff that
Yeah.
works, and then you even find a new component class. Yeah, that's
Yeah.
great. And then with these diionic forms, you said that there's a lithium, and you also try to swap that lithium for other metals. And
Yeah.
ideally would be also have aluminium. So in the end, when you decompose this complex, then there's just no chance of lithium because there's none.
Yeah.
But what was the approach on this? How could you change the second metal?
With transmetallation reaction. So my idea was I can take this complex and react it with AlCl3, other aluminum hydrides, a bit of everything, to be honest, because there wasn't any
Yeah,
research on it. So we were literally like
yeah,
exploring. I tried to react it with these different chemicals, but from the NMR I couldn't really tell what was going on. Something was happening. For
yeah,
some of them, there is something interesting and promising. However, the NMR for these complexes is quite noisy, I would say. There are a lot of sharp peaks, and you're like, what's going on now? So that was tough. I tried different crystallization. So if you read my PhD thesis, there are many
yeah,
reactions on that, but not all of them are, let's say, successful. I showed some NMR in the thesis, and I was like, this is what I got. That's the NMR. I can try to guess, but again, I can't really prove any
yeah.
product.
Especially when it's new and you don't have anything to compare to, it's much more difficult.
Exactly, exactly. So I tried my best. I discussed it with the examiners as well. They were like, "We got it. You did a
Yeah.
lot, but untractable mixture, we
Yeah.
call it."
Yeah, with these metal
Yeah,
complexes, sometimes it's also with the NMR, it's difficult because depending on how they are oriented, you get different
yeah,
peaks in the NMR. And when you just
yeah,
have several different orientation complexes in your solution, which can also happen, then yeah.
yeah. You can have racemic mixtures as
Yeah,
well.
true.
So
Or within the time frame of the NMR, fast and slow
yeah,
rotations, which also mess things
yeah,
up. And
yeah. There are a lot of low temperatures NMR in that thesis. Sometimes I don't even want to look at that anymore. But yeah, we tried our best to like cool it down and freeze some
Mm,
movement, right? Or like slow down some movement to see something. But for some of them, it was just
mm.
unsuccessful. So, but that's part of the research. Like when you explore
Yeah,
blind,
of course.
that's the
That's
risk. That's why then I changed
yeah,
ligand towards
yeah,
the end.
yeah. That's always good to have a backup.
Yeah,
Yeah,
just in case, or fresh
yeah,
things to experiment.
yeah. So, with your research in mind, where do you see this in the future application? If this idea of having the metal organic complex working with this aluminum, how would this be applied in the future?
So first, I would say we need more
Mm.
literature on it. So hopefully, the group is going to publish more
Hmm.
things, and because they work with different
Yeah,
metals. Like even me, I collaborated with other people as well on different metals. So let's say the research is slowly like
yeah.
discovering ways of depositing it. But once it works, I mean, we managed to do the first
Hmm.
non-pyrophoric precursor. So ideally, if it's user friendly, I can see this applied in the
Hmm.
industry for printed
Hmm.
electronics. So that's a way of doing smaller and smaller
Yeah,
electronics. But it's not just the size, it's more like the user friendliness
yeah,
of that. Like you don't need sophisticated equipment or glove boxes, or
yeah.
hopefully like you just take it, spray it, heat
Done.
100
Yeah,
degrees, done.
yeah. That.
Conductive. That's
Yeah,
mind blowing. But
yeah, and it would be a lot more safe because if you have safer components, there's
yeah,
also a big
yeah,
part of the green chemistry that you want to swap out
yeah,
more dangerous compounds for less dangerous ones.
exactly.
Yeah, and it's still relatively fundamental research, which lays the
Yeah,
basis for future research, and then other groups can pick up on that who
improve it.
focus more on
Yes,
the printing part, and then yeah,
yes,
would apply that.
yeah.
And
Because we are like Caroline Group is quite expert in
mhm.
Schlenk chemistry. So all of us, we do pretty
Yeah,
dangerous chemistry, I would say, from low valent aluminium sometimes to just aluminium complexes. And it's an expertise quite
yeah,
dangerous, I would say.
yeah,
So we can do it, and someone else
yeah,
can use more user friendly
yeah,
precursor.
yeah. That's also a great thing because then it's an advantage and disadvantage at the same time. I would say if you do chemistry that not a lot of other groups can do, it's like you have
Yeah,
less competition, but you also have
yeah,
less opportunities to look at other people's work. Like in our
yes.
group, we also did even cyanide chemistry. So
Wow.
that was pretty much one of the few groups worldwide who do research on this. I
Mm,
mean, I also did Schlenk chemistry and did some phosphines for metal complexes, but I think they were not as reactive as the aluminum. Once I worked with
okay.
metal aluminum, and that was
That's
there was even within the Schlenk, like the inert Schlenk setup, it was smoking. So
yeah, yeah, yeah. No, that's extremely dangerous. That's why we're like, if we can
yeah,
transform that in something more user friendly, yes, you will have a powder that maybe bubbles a
mhm.
bit, but
It will not catch fire
do you
instantly.
really
Yeah,
want to compare a bit of bubbles with fume and the nitrogen is
yeah,
fuming? I'm like,
definitely.
yeah, that's why.
So Schlenk chemistry is also what was the idea for your Instagram and TikTok profile, right?
Yeah, 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 yeah.
So,
Yeah. Well, it all started. So first, I mean, Caroline, she's not the only one doing
mhm,
precursor chemistry. It's quite popular. We have Claire Kalmart, the head of department. She has a big group. She works with
mhm.
CVD, deposition. So she's not the only one. It's just like aluminium precursor is quite
Yeah.
difficult. But yeah, I just started during the PhD making some videos on my
Yeah.
personal account because I just enjoyed the like sharing the
Yeah.
showing the lab to the people. But then on my personal account, it was a bit
Mhm.
messy, right? Like on Instagram, you have what you do, your
Yeah.
hobbies, the chemistry lab. It was a bit, the algorithm didn't really understand what I was showing on the account. So just for my colleagues, let's say.
I mean, it is very exciting research, and also for chemists who just do other kind of research. This whole Schlenk setup, I think, is always very fascinating.
Yeah. And then I decided to go more vertical. I was like, okay, I'm going to open an account on TikTok
Hmm.
last year when I'll go vertical on that because anytime I talk about chemistry to
Hmm.
my friends that are not in
Yeah.
science at all, if they don't get bored, it's like I can't really
Yeah.
I can't really say much because on the second sentence or word they're like already
Yeah.
somewhere
Yeah.
else, especially when you talk. So but then when I show the videos, like from the kids, like my
Hmm.
nephew's age, so 6 year old, to old people, when you show a video and you're like, look what I made
Yeah.
today, that has a power on this. Like it's cool, at
Definitely.
least. Ugly, difficult, dangerous, but cool.
Yeah, but showing that is also then interesting. It's like you can have a lot of color changes.
No, but it was nice. Like sometimes I posted, I don't know, videos of the flask with the
Mhm.
liquid stirring, and people were like, "Oh, what are you making? Whiskey, ice cream?" Like. But that
Yeah.
attract people, and that's how it started. Because I was like, I can just show it
Mhm.
to everyone and bring lab chemistry closer to people. Because there are a lot of people doing
Yeah.
shows. I also did some outreach events with
Mhm.
UCL. We did, I don't know, the red cabbage
Yeah.
juice.
Classic.
If you add different substances, it
Yeah.
changes color. But that's nice. But it's for me, it's like that is not the chemistry we
Yeah.
actually do. So I was like, I want to bring my space out
Mhm.
there to the people because no one knows what we do in
Yeah,
the lab.
exactly.
They don't even think we're working, to be honest.
And
It's not even a job.
there are very little accounts on social media which actually share chemistry research. When
Yeah,
I also started with the podcast, I was first looking on the podcast platforms. Okay, I kind of miss chemistry, so I want to listen more to like chemistry stuff to keep up. And
yeah,
there were just so few. There were just some, and they were also in very specific niches, which is okay,
yeah.
but they were not really the ones I was interested in. And I was like, okay, I would just start one of my own, then
I have to do it if no
yeah,
one is doing
and
it.
also connect them
Yeah,
to other researchers and getting this chemical research a bit more broader audience because
yeah.
chemists are very good in doing the research, but sometimes the communication about it is not in their
It's
focus
such a big
because,
problem.
well,
Yeah.
you also are very busy in the lab, and then you might not think about to share this on social media or so, or might think that other people would not be interested. But in your case, you already gathered quite a large audience, and
Yeah, yeah, I was lucky on that. I mean, academics can be very elitist as well, I have to
yeah,
say.
definitely.
I'm not going to defend academia that much, but that's the problem, right? Like if you communicate too much, or if you're too
Mm.
funny, too colloquial, that means you're not smart enough.
Ah, yeah, right. That's a point.
That's a
Yeah,
big problem, especially at
yeah.
conferences. That's why all this pressure, all this stuff, when it's my creativity started on the PowerPoint
Hmm.
presentation. I love to do
Yeah.
PowerPoint presentation, but also challenge myself, right? Like maybe I see on
Hmm.
TikTok tutorials to make
Hmm.
animations, and I'm like, if Apple, when they release their product, they can do a keynote that it's
Yeah.
cool, why can't I do a keynote that is as cool
Hmm.
as Apple and not
Yeah.
boring? So that's how it
Yeah.
started, the creativity on that side. And then I realized that, yeah, I mean, I tried to keep it a bit
Hmm.
hidden, to be honest. I didn't spread the word that much in the department because people tend to think, oh yeah, you do funny videos, then okay, you must not
Yeah.
work much, or you must not know a lot about
Hmm.
your field. That's the stigma.
And I think that really depends also on the field, but I think the competition also sometimes plays a role that I don't want to share any of my work because someone might scoop me.
Yeah, but I noticed that you don't have to share everything, right? So you can always share something, a teaser, and that doesn't mean you're telling them how you
Yeah,
do
of
it.
course.
You're just showing what you do and make it cool. But the problem is that unless you're big enough, you're not really getting
Yeah.
involved in that. Like PhD students, they do poster session at conferences. If they're lucky, they can do some
Mm-hmm.
talk, short talk. But it's all about, the big
Yeah.
scientist, the Nobel Prize, and that's fine. I mean, I got a lot of inspiration from these
Yeah.
talks and motivation, but still, like, what about us? All of us in the lab every day. Because when I tell my friends, I'm like, yes, I'm in the lab. Some of them think that I'm 24/7 in the lab, and that's it.
Yeah.
A- And they're like, yeah, you don't do admin work. You don't do any of that. I'm like, that's part of the
Yeah,
PhD,
especially
you
at
know?
the PhD. I think when you're like a professional researcher in some research institute after the PhD, then it might be a bit different. But also
Yeah,
in Germany, I did a lot of teaching lab courses, teaching classes, and that
yeah,
adds up to the whole workload, definitely.
exactly. So I'm just happy to share it. Like, that's how it works. And nobody talks. And the scientists online are often
Yeah.
biochemist, biology, saving the world with treatment for
Mm.
cancer, anything. Great. But there's no pure
Yeah,
chemistry.
that is really true.
So, what is inorganic
Yeah.
chemistry? They always think about, I don't know, the rocks, the things. And I'm like, yeah, but
Yeah.
yes, but we have
Yeah.
labs that take care of that. So,
Yeah,
yeah,
that's
that's why.
maybe because people think it's a bit more relatable. So, I mean, when you do
Yeah,
cancer research, everyone somehow knows what that is.
yeah.
But when you do some metal organic complexes, that's even,
You already
yeah,
lost the audience on the
you
third
even
word.
lost
Yeah.
a lot of chemists there.
Yeah. Yeah, but we can make it like my mission,
Hmm.
let's say, is like we can make it fun because you don't have to tell me all the conditions you used, all the ratio, all the stuff you used. You have a broader audience. Okay, I'll show you my
Hmm.
crystals. They're super nice at the
Yeah.
microscope, right? Like,
To break down what you do in a very simple way so other people can understand it also helps you to really think about it differently, sometimes even discover
yeah,
stuff that under this lens you can see,
yeah,
but when you just focus on your work, you don't.
yeah,
Talking about it is always difficult if you have to explain it to someone who is not in the field, I would say.
yeah. But also, I have to say, also in conferences, what is this need of using such fancy language to explain what you do? Because you have 12 minutes
Yeah.
presentations, right? I agree. We need specific language. There is a reason. All the nomenclature of the chemicals that we
Yeah.
learned at the beginning, like it's crazy, but let's use it. Fine. But also, we don't need to be as fancy because you're gonna lose your audience because people are distracted. Even if it's a very niche
Mm.
conference where people want to network, if you're not a big name, so if
Mm.
you're no one, as the majority of all of us, then you go there, you use fancy language, and people scroll on the
Yeah.
phone, are distracted, bored, is after lunch. I always say use less fancy jargon,
Mm.
but keep the audience focused on your presentation.
Also, less stuff on one slide. There are so
Uh,
many presentations on these conferences where they have
ex-
like every millimeter of space is used by some
yeah,
kind
with
of
words.
figure or
Yeah,
something, and it's
yeah.
overwhelming. So,
And also, I hate this basic presentation divided in
yeah.
four parts. I'm like, we
Yeah.
have enough of that. It's like at least the young
Yeah.
generations, we can do
Yeah.
better. And for free, because if you go online, you can find many tutorials
Yeah.
to make it cool.
And also a plus part of having a really good and entertaining presentation is that afterwards people will remember it. They will
Exactly.
come to you
Exactly.
and talk, yeah, I liked really this part, because that's
Yeah.
how you make them remember. When it's just very not fluctuating, then they will just, as you said, scroll on the phone.
Exactly. Yeah.
Yeah.
I mean, if they want to dig in the topic, they can always log
Read the
in
paper.
on Google
Yeah.
Scholar and
Yeah.
read the paper. Supporting information, they can read all the data. But I don't think a conference is the place to do
Hmm.
that unless, I don't know, for a couple of slides, you have a very specific topic you want to share, discuss, or
Hmm.
flex your knowledge on something, but not the whole presentation, let's say.
Also, this flexing the knowledge, I think that's what a lot of people do. That doesn't really help. It's like
It
the
doesn't.
audience, you lose the audience, and then who are you flexing to?
Yeah, 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 to yourself. But I have to say, above a certain level, the very big people like Nobel
Hmm.
Prize winner or like people at the end of their career, when they do talks, and sometimes it's like main
Hmm.
speaker, so 40 minutes talk. Yes, they have those 10 minutes of very difficult chemistry, but it's always very
Yeah.
inspiring, more broad, more. I'm showing you the
Hmm.
mission, the pathway I followed. I find, why can't we
Yeah.
do it? Like,
Well, they also have a lot of reps if you think about it. It's so many.
true. That's also true. But it's all about the
Yeah,
storytelling.
definitely. What tips would you have for the audience in terms of storytelling for science? Do you have some?
For presentation at events, conferences, I would keep it simple, always simple. As a non-native speaker, English speaker, I always suggest, I would love to use fancy jargon and fancy words, but it's not my
Hmm.
native language. So I would rather keep it simple. Don't learn a script by
Yeah,
heart.
that's
Have your bullet points, keywords that guide you through your presentation. So if you have a blackout, you look at your slides and you can pick up at any
hmm.
point.
Yeah, that's
Because it's fine for one time, maybe at the beginning you
mhm.
learn everything, you're stressed out, but long term, it stresses
Yeah,
you out, tires you out. And also, it might happen that day when you have a blackout, you're tired and you forgot what you're talking about. Whereas if you have a slide, you're like, okay, what's this about? I have
yeah,
to say this. What's next? I don't know. I'll see it and I'll
yeah,
tell
yeah,
you. Like,
definitely.
so this for events. For social media, I mean, for social media, it depends on the aim.
Hmm.
So you want to be funny, be yourself. I noticed that since I started showing
Hmm.
myself in the videos and maybe also talk, people started coming to the account. So authenticity, and also I know it's difficult to talk on a camera, especially the first time. It's awkward, you're weird, you look at yourself, you're like, what am I doing? I can't even hear my
Yeah,
voice. But as soon as the more you do it, the better it becomes, and people
yeah,
like that.
yeah. Definitely, the authenticity is really important. If you just try to be someone else, that might work for one or two videos or
Yeah, but
whatever,
not
but not
always.
not
Yeah.
for a long term.
Also, like, I don't know, I'm quite noisy,
Mm.
messy, like exuberant character in the lab. So if I try to be more formal and authentic, I'm just
Yeah,
colder. So there's no
yeah,
aim in that. And also, if someone want to criticize what you do online, there will always
yeah.
be a reason to do it. So
Either way,
just
yeah,
be yourself. Because sometimes I don't use gloves, and people are like, "You should wear gloves." I'm like, "Do you know what I'm doing?"
yeah, exactly.
Right? I can't wear gloves every time in a chemistry lab because
Sometimes it's even worse. Yeah,
it's even worse because they're not like
yeah,
a shield. Like things go through, and it's better sometimes to not have it and wash your hands
yeah.
more often. So that's a hot topic in the videos.
Okay, yeah, thank you. And in this episode, I want to start a new tradition for closing the episode. And what is your favorite discovery in chemistry?
That's a tough
Yeah.
one. Are you sure you want to start with me? My favorite discovery, I don't really know because they're all great and amazing. I mean, I would go broad, not specific. I would say polymer, even if we live in a world no plastic,
Yeah.
or get a metal bottle rather than, or a glass bottle rather than a plastic one.
Yeah, that's a good one.
I say I'm a fan of polymers because they changed our life
Definitely.
if you think about it. Your shoes, anything around you.
Yeah. There's almost nothing now, I would say, that comes without polymers. Like it's a
Yeah.
packaging
The
or
problem
something.
is we don't know how to recycle
Yeah.
them and we make them from the wrong
Yeah.
source. But I mean, now we know we can progress on that, but that was my favorite discovery.
Yeah, that's definitely a very important one. For me, I would say it's the Haber-Bosch process. It's like the
Okay.
industrial synthesis of ammonia, which makes all this fertilizer production possible and
Yeah.
feeds about 2-3 billion people in the world, which would not be possible
Yeah.
without that.
True. That's true also. Then the problem again is the abuse
Yeah,
of that, right? Is the quantity, is not the actual
yeah,
discovery.
yeah, that's true.
But yeah,
But
I agree.
yeah, then
That's
thank
nice.
you very much for taking the
Thank
time. That
you.
was a really fun discussion. And then,
Yeah.
yeah, I will also put the links to your socials in the show notes. And yeah, thank you very much.
Thank you very much.
I hope you enjoyed this episode. Thank you very much for listening. Don't forget to hit the follow button wherever you're listening to this. It really helps the show more than you think. Also, check out Leonardo's Instagram and TikTok account. He has really fun content on science and chemistry. If you also want to share your research in the podcast, then let me know. Either find me on LinkedIn or send an email to contact@innovateandreact.com. Until next time, keep innovating and stay curious.